Hello everyone and welcome back. I'm Mahanur and today we'll be continuing on with the chapter of kinematics. Now, up to this point, we have basically learned all that we can about one-dimensional motion, where we saw how we can conduct a qualitative analysis of different types of motion as well as a quantitative analysis of different types of motion through equations and graphs and things like that. All of this applied very easily to one-dimensional motion like I just mentioned. So that would entail any object that's moving either horizontally or let's say an object that's moving vertically. Now we're ready to dive into the next phase of this entire chapter, especially in AS level physics, where we will step out of one-dimensional motion and address two-dimensional kind of motion. The name suggests everything that we need to know about this type of motion. Two-dimensional motion implies that we'll be dealing with motion where an object covers two dimensions together. So what would that moving object look like if it were moving horizontally and vertically at the same time? Well, if you wanted to draw an arrow to represent that, all you would need to do is draw something that has a horizontal and a vertical component combined. Something like that, let's say a velocity vector, would look like this. It might not seem as if there's any horizontal or vertical components hidden within, because if you think about it, even this is simply a one-dimensional arrow. But it turns out that you can actually break this down into what we call rectangular components. It can be broken down into rectangular components. Any vector can be broken down like that. We'll be specific to just this velocity vector. The word rectangular here implies that these two components that we'll draw are going to be what we call mutually perpendicular, meaning they will be perpendicular to one another. Again, at this stage it might not seem that obvious, but we can definitely draw it in terms of the following diagram. So it's basically this first diagram enlarged like so. Since this is tilted, we can represent this amount of tilt in terms of an angle theta. Now, we can draw one side of this velocity vector v that's adjacent to this angle theta, which we can draw horizontally, vh. And then we can draw one that's mutually perpendicular to this horizontal velocity as follows. So it would be perpendicularly upwards, and we'll call this VV. VH is what we call horizontal velocity, while VV represents vertical velocity. Now, if we recognize this triangle that we've made very carefully, and knowing that VH and VV both are perpendicular to each other, we recognize that what we've constructed is nothing but a right angle triangle, in which case I can use any one of my trigonometric ratios to figure out what VH and VV are. Now for VH, I can use the cos theta expression, which would be adjacent over hypotenuse, VH over V. Rearranging this, I simply get VH equals V times cos theta. Whereas for the vertical velocity component, I can use the sin theta expression as VV over V. Rearranging it, vertical velocity equals V sin theta. And so these are my rectangular components that I was mentioning just before, right? Now, as simple as this was, we'll be looking at one specific kind of two-dimensional motion a bit more extensively. That's what we call projectile motion. Now, when I say specific, it's actually obvious from the way we define or describe projectile motion. Think of it as a specific or a special kind of two-dimensional motion wherein an object has uniform motion in one direction and non-uniform motion in a perpendicular direction. Not only is this kind of projectile motion special in its definition, wherein you have uniform motion in one direction and non-uniform motion in a perpendicular direction, but it's also unique in the shape of the path or the trajectory in itself. We can draw that or represent it as follows. Consider this as level ground. Suppose you have, let's say, this ball that's being sent in this kind of a path, and let's say it's being launched with that tilted vector v, and we already know it has two perpendicular components, horizontal velocity vh and vertical velocity vv. The special thing about this path or this trajectory is that it has a shape that's very much like what we call a parabola, and therefore this shape in itself is also called a parabolic path. Now, with this understanding of the path, we should also know when is it, or based on what certain assumptions or criteria do we get this kind of a parabolic path to begin with. In short, there are two assumptions that we need to follow. This path is based on two assumptions. I list them out first, and then we'll discuss each of their implications one by one. The first assumption is this, that there are no horizontal forces acting on the projectile. The projectile being the object that's being sent into projectile motion. The second assumption is that there is only one vertical force that's acting on the projectile. That is the object's own weight. Weight is the only vertical force acting on the projectile. Now let's study their consequences one by one. Now, when we claim that there are no horizontal forces acting on this projectile throughout its motion, what we're saying is that automatically there is no horizontal acceleration either. This is nothing but a consequence of Newton's second law of motion, where we recall that resultant force equals mass times acceleration, right? So if there's zero force, there's obviously going to be zero acceleration, right? So it's basically that interpreted right over here. And since there's no horizontal acceleration, that automatically means the horizontal velocity is constant. And so throughout this above drawn projectile motion, at different points, the velocity vector for the horizontal component will not change at all. So notice how I maintain the same direction and the same magnitude throughout. Right? Now we have the second concept, the second assumption, that weight is the only vertical force acting on the projectile. Now this makes sense if we think about it, right? Because whether your object is moving horizontally or vertically or in any other kind of special motion, weight is the gravitational pull that acts on it. And that's something that we definitely can't ignore unless we're launched into deep space, right? So the vertical force has to be equal to the weight. And when you once again use Newton's second law, we realize that the vertical acceleration will be equal to the acceleration due to gravity. Now the special thing about this value is that it actually stays constant. So now you have constant acceleration in the vertical direction, which is to say that the vertical velocity will definitely change, but it will change in a uniform sort of fashion. Now, will it continuously increase or continuously decrease? Well, it actually depends on the motion of the projectile itself compared with the direction of the weight. Now, when you think of the weight, that will of course always be vertically downwards. Now, for the first half of the projectile's motion, the projectile is being sent vertically upwards, right? Now that upward motion is obviously in opposite direction to the weight itself. Therefore, there will be a decelerating sort of an effect where basically when the weight is downwards, the acceleration due to gravity will also be downwards as well. Acceleration A, which we know is equal to the acceleration due to gravity, that too is pointed downwards. So, if the projectile is being sent vertically upwards, then there will be a decelerating sort of an effect where the object will be slowing down until it reaches the top. And so, that velocity vector will be seen to decrease until it reaches 0 at the very top. But after this point, as it continues to fall down due to the influence of weight, now the velocity vector is in the same direction as the acceleration vector. And so there will be an accelerating sort of an effect where the vector will be seen to lengthen, which is simply the effect of the vertical velocity increasing beyond the value of 0. So in short, or in summary, what we've concluded is that when the projectile is going upwards, what we conclude is that there will be a decelerating effect. And so the vertical acceleration will be equal to minus the gravitational acceleration, whereas when going downwards, due to the same direction phenomena, there will be an accelerating sort of an effect, and so the vertical acceleration will be the regular positive acceleration due to gravity. And so we have sufficiently understood how the horizontal and the vertical components each are being influenced due to one force or the other throughout this projectile motion. Now this is as far as the qualitative analysis goes. Now how do we quantify things? For that we will once again rely on equations. Here, since the horizontal and the vertical components both are independent of each other, it makes perfect sense to treat each of them individually. When it comes to the horizontal component of motion, there is only one formula that you can use, considering that horizontal velocity is constant. It would simply be the definition of velocity, which is horizontal displacement divided by time. On the other hand, for the vertical component, since we have constant acceleration, we immediately remind ourselves that any of the Shewhart equations apply here very easily. Now, of course, depending on the kind of question, we can have, of course, different approaches of how to solve questions, but there should be an understanding of two other quantities that are associated with projectile motion. The first one is maximum height of the projectile. This is a vertical displacement, to be specific, and it's the highest point of the projectile, which is usually its peak. That can be drawn diagrammatically like so. Suppose you have your projectile V tilted at an angle theta, and let's say you have a parabolic path like so. The maximum height would be somewhere like right here, represented with capital H. Now in this case, we can see how the maximum height itself is a vertical displacement. And so when it comes to writing down or calculating an expression for this maximum height, we'll be relying only on vertical components. In which case, we can forego with the vertical velocity, with the velocity vector itself here, and focus on the vertical velocity. I can immediately figure out what the vertical velocity initially is as simply the expression in terms of v and theta that I have, that is v sine theta. That's my initial vertical velocity. At the very top, at which point I want to figure out what this maximum height h is, I know that my vertical velocity is 0 because at this stage there is only the horizontal component of velocity that exists and there is no vertical velocity component. So vertically speaking, that's my final velocity value right here. So I want to figure out an expression of h such that it doesn't rely on quantities like time. There is one formula I can use, that is 2as equals v square minus u square. But I'll have to make appropriate adjustments over here. 2 stays as it is. In place of acceleration, I can write minus g, minus because in this first half of the motion, the projectile is being sent up while the weight of the projectile is pointed downwards. So due to the opposite direction, we know for a fact that there will be deceleration involved here. And so for displacement s, I can write the maximum height that I wish to find, h. The final vertical velocity is 0 and the initial vertical velocity is v sine theta whole squared. So now it's just a matter of simplifying things. Minus 2gh equals minus v square sine square theta. The negative signs cancel. And so I have an expression for maximum height, that is v square sine square theta divided by 2 times g. Great. Now let's see another quantity that's associated with projectile motion, this time specifically to horizontal motion, that is the range of the projectile. Think of the range of the projectile as the total horizontal displacement of the projectile. That can be drawn once again as follows. You can take the same path like so, same projectile v tilted like so, with the following kind of parabolic path, and this time the range would be the total horizontal path like so. Since this is strictly horizontal, it makes sense to then remind ourselves that here we'll be relying only on horizontal motion. And so we can forego with any vertical components and simply split the velocity vector v tilted at an angle theta to its horizontal component vh, which I do know would simply be v cos theta, right? And so if I do want to figure out the range r, it's just a matter of rearranging the definition of velocity being displacement, specifically horizontal displacement, divided by time duration. Except this time vh would be v cos theta. The total displacement in the horizontal direction would be the range r, and for t it will be specifically the total time for the entire projectile path. And so the range is simply v cos theta times total time duration tt. Great. So not only have we understood the fundamentals of two-dimensional motion and how we can break vectors down like so, we saw what projectile motion looks like, what assumptions lead to specific special features of projectile motion and its velocity components, and then we saw two quantities that we can associate it with projectile motion. Now we're well equipped in seeing one simple practice question and see how we can apply our knowledge. So here we have our practice question. A motorcycle stunt rider moving horizontally takes off from a point 1.25 meters above the ground, landing 10 meters away as shown. What was the speed at takeoff? So I want you to pause this video for a moment and attempt in solving this question first. Give it a fair try, treat both horizontal and vertical components of this motion separately, and see if you can approach the answer. And later on, we will solve this question together, starting now. Alright, let's discuss this together and see where we are headed. Now, we know this is a parabolic sort of a motion, right? It's actually more specifically a half parabola. Normally what we've been dealing with so far are complete parabolic paths that have a board shape like this. What we see here is actually half of a parabola, meaning instead of starting from a tilted fashion, it's already starting from a point that's horizontal at the start and then obeys the usual parabolic path halfway through. So at the start, we expect that takeoff speed to be nothing but the horizontal component of velocity, which we know for a fact that stays constant throughout. And if this is staying constant throughout, there is but one formula that we can apply over here. That is that the horizontal component of velocity is simply the horizontal displacement divided by time for that projectile. The horizontal displacement, if you think about it, is already given. That's the range. That happens to be 10 meters. But we don't know what that time of the projectile is. For this, we can rely on vertical components. It makes sense why we can do that to begin with, because even though there are horizontal displacements, vertical displacements, and different velocity vectors as well, there is no such thing as horizontal time or vertical time, right? Time will be the same whether you're moving horizontally or vertically or both at the same time. And so we can figure out what the time duration for this entire projectile is using vertical components and then apply it to this equation. So now let's look at the vertical pieces of information that we do have. Now for vertical component, what do we have? Since this projectile is falling downwards, there will be an accelerating sort of an effect. So the vertical acceleration will definitely be equal to positive the gravitational acceleration. We know there is a vertical displacement as well, 1.25 meters. We know the initial vertical velocity as well. That's simply 0 because at the start it's completely horizontal. So there is no vertical component to be seen. We can use these values to figure out what the time of the projectile is using a very simple equation, one of the Szilard equations in fact. That would be S equals ut plus half at squared, where this time we can plug in the numbers. S would be 1.25 meters, ut vanishes because u is 0, half times 9.81 times t squared. So simplifying this further, I get 1.25 times 2 divide by 9.81 equals t squared. And if I take a square root on both sides, I get t to be as follows. Pause. The value that we get is 0.505 seconds. Now that you have your value of time, we can plug it back into our expression for horizontal velocity, which would be 10 divided by 0.505, and that will give you 19.8 meters per second. And so that's basically the closest answer that we have over here is 20 meters per second. And so the answer is D. So here see how we were able to treat individual components of horizontal and vertical motion in a way that we can use one or the other to figure out our final answer. Thank you.